In this NMR example, we have C9H12, and we have a singlet here, we've got a doublet here, and we've got a multiplet right there. We have the integration 516, okay? And so it'd be 516. Notice something else that is helpful in this particular example. We can calculate the degrees of unsaturation, which you can see in some of my other videos if you don't know how to do. But if this was fully saturated, it would be C9. 9 times 2 is 18, plus 2 is 20. C9H20 would be fully saturated, and so we're, let's see, how short are we? We're short by 20 minus 12 is short by 8. If you divide that by 2, that's 4 degrees of unsaturation. That means there's a if between rings and double bonds, or some sort of multiple bonds, there's 4 of those. So for example, there could be 2 double bonds and 2 rings, or 1 ring, 3 double bonds, something like that, okay? Now, another thing that kind of clues me in that there's like rings or double bonds, I have a peak way up here at 7. Whenever you have a peak pretty high up, I start to think of a benzene ring or some sort of aromatic, okay? So this kind of clues me in. I think I might have something like that, okay? And then I have a multiplet and a doublet, so I'll have to see what to do with that. Okay, now since this 5 plus 1 plus 6, that sums up to 12, and then there's 12 hydrogens, it tells me exactly the number of hydrogens here. So I know I have 5 hydrogens here, so it looks like I have 1, 2, 3, 4, 5, and then something out there, okay? So I believe I do have an aromatic. It fits the shift. Everything looks pretty good. Most likely this is whatever is closest to the aromatic, or bonded directly to it, and where this is just a normal alkane. So this has an integration of 1. I'm thinking this is a CH group bonded to 3 things. So one of these probably is the aromatic, and then I have this is the aromatic. And then I have 2 mystery things here, and then one of them is the H. And it's given a multiplet. Not only, I mean, it is close to aromatic, but probably most importantly, there's some sort of carbon groups with hydrogens on here that's causing the multiplet. Okay, finally, let's go over to the doublet. Let's see what I've used. I've used 1, 2, 3, 4, 5, 6 carbons here, 7 there. I'm left with 2 carbons left over. There's 5 hydrogens here, 5, 6. I've used 6 of the 12 hydrogens, so it looks like there's 2 carbons and 2 hydrogens left. 2 carbons and, 6 hydrogens. So this looks like to make this symmetric, most likely it's 2 CH3s. Let's see if that would work. If 2 of these were CH3s, they'd be next to 1 single hydrogen, and 1 hydrogen, add 1, that'll give a doublet. That makes a lot of sense. If this is next to all these, 1, 2, 3, 4, 5, 6, plus 1, that would give a septet, or 7 peaks. Let's put that all together and see if this all makes sense. Okay. So first of all, we got the ring. It's highly shifted. That's what we expect. Integration of 5, that works. This is shifted over a little bit because it's close to the ring. It's giving at least a septet, because 1, 2, 3, 4, 5, 6 plus 1 is 7. That's right here. And the least amount of shift is these that are furthest from anything, furthest from the ring. They'll give a doublet because they're close to this. So this 1 hydrogen plus 1 would be a doublet. And that's an integration finally of 6 for the last one. That seems to work out nicely. This is our structure right here.